These ironworkers' cottages were built more than 200 years ago. Crude by modern standards, with 2 tiny bedrooms and a shared outside earth closet, these houses were quite comfortable for the time. The ground floor was made from stone flags, or sometimes clay tiles, laid directly over levelled and compacted earth. Carpets were virtually non-existent, and people made do with homemade rugs and matting. Stone flags and clay tiles were easy to clean and didn't suffer much if they got wet. They were, however, cold and had an uneven surface. These middle-class townhouses were built about the same time. Most of these had basements, again with stone flag or clay tile floors. Towards the end of the 19th century, the standard of working-class housing slowly improved as planning controls and building acts became more stringent. In addition, cheap imported softwood became readily available. And by the early 1900s, most new houses were being built with timber ground floors. Timber floors were warmer and drier than flagstones and a much better surface for carpets and linoleum. Timber floors consist of a series of timber joists covered with timber boards. The floor is not in direct contact with the ground and is often referred to as a raised timber or suspended floor. In a typical floor from about 1900, the joist ends were usually built into the solid external walls for support. To keep joist depth to a minimum and to preclude the need for long, expensive timbers, additional support was provided by intermediate walls called sleeper walls. These could be built from brick or stone and were sometimes honeycombed to help ventilation of the floor void. A strip of timber known as a wall plate provided a level surface and a good fixing for the joists. Sleeper walls were sometimes built straight off the ground or on shallow foundations. Ideally, the ground level below the floor should be higher than outside to prevent the risk of ponding and flooding. The joist ends were susceptible to penetrating damp because in most cases they were only protected by half the thickness of the wall. The lack of effective damp-proof courses meant that joist ends and wall plates were also susceptible to rising damp. The bare earth or rubble infill beneath the floor was often permanently damp, and to prevent conditions which could lead to rot, the floor was ventilated. Terracotta or cast iron vents allow air to flow beneath the floor in an attempt to keep the underfloor space dry. In many houses, there aren't enough vents to do this successfully. A typical terraced house might have 2 or 3 vents at the front, but only 1 at the back. Ventilation at the rear of the property was often restricted because the scullery, where the washing would be done, usually had a flagged solid floor. This meant that a large part of the floor void, usually along the party walls and under the stairs, was poorly ventilated. When surveying old houses, these areas require careful inspection. In some houses, clay pipes laid under the scullery floor provided a through flow of air and better ventilation. Even if there are enough vents, problems can still occur if vents become blocked or if garden or paving levels change. In some cases, the vents are so low that water from paths can actually run into the floor void. In most Victorian houses, the joists were covered with square-edged softwood floorboards. Over the years, as the timbers naturally dried, the boards would shrink and twist. This could damage floor coverings, and the unsightly gaps between the boards could make the room drafty. In some houses, solid floors weren't just confined to the scullery. In better quality housing, the hall floor was often a solid concrete slab laid directly on the floor and finished with decorative tiling. A tiled floor provided a very durable finish. It also signalled prosperity and good taste to all who walked over it. The raised timber floor was used in millions of late Victorian and Edwardian houses. Improved building standards in the years after the First World War did, however, lead to changes in the way that these floors were constructed. No longer were joists built into external walls. By keeping the joists clear of the wall, risks of penetrating damp were avoided. Risks of rising damp were reduced by the introduction of effective damp-proof courses. Additional protection was provided by forming a concrete slab over the bare earth. This helped to keep the underfloor space dry. Many of these houses had tongued and grooved rather than square-edged floorboards. The interlock in tongued and grooved boards reduces twisting and eliminates drafts. They are, however, not as easy to lift for maintenance purposes. In the 1960s, timber floors were still popular. This example may not be textbook construction, but it hasn't given rise to any problems in more than 40 years. There's no wall plate, which is unusual. The joists sit directly on a course of engineering bricks laid on a bitumen felt DPC. The sleeper walls, however, are honeycombed to help cross-ventilation. Ground level below the floor is quite a bit lower than the surrounding garden. After long periods of heavy rain, water finds its way into the void. The tide mark shows just how deep it can get. Timber ground floors are not very common in modern construction, but they are quite acceptable. Unlike their earlier counterparts, modern floors are insulated against heat loss and are normally finished with sheet materials such as chipboard or strand board. In addition, the building regulations are more rigorous in terms of underfloor ventilation. Insulating older floors is quite easy and certainly cost-effective. The floorboards on this 1920s house have been carefully removed, and an insulating quilt has been suspended between the joists. The glass fibre quilt is wrapped in a vapour-permeable polythene to make it easier and safer to handle. Glass fibre can be a skin irritant. When the quilt was complete, the boards were relaid. An extra board was required in each room because the boards were relaid with finer gaps to improve appearance and help reduce drafts. This particular floor was then sanded and varnished. An alternative is to use rigid foam or polystyrene boarding supported on battens. If possible, the edges of the floor should also be insulated to prevent the risk of cold bridging and condensation. In the period following the Second World War, timber was in short supply. This shortage of materials, together with a shortage of skilled labour, led to the development of a number of new building techniques. The use of concrete floors, which had in fact started on a limited scale in the 1930s, became the most common form of floor construction. A typical ground-bearing concrete floor from the 1970s and 1980s has four main components: A hardcore bed makes up levels and provides a good firm base for the slab. A polythene damp-proof membrane prevents capillary action. An in situ concrete slab forms the structure, and a sand and cement screed provides a smooth, level finish for tiling or carpets. Later floors from the mid-1990s to the present day also include floor insulation. Once the topsoil has been removed, the trenches dug and the foundations poured, the walls can be built to DPC level. Concrete blockwork is cheaper than brickwork and is much more likely to be used below ground level. It's normal to use cavity construction, although solid walls are equally acceptable. Before the floor construction can commence, it's important to lay and test any drains which run beneath the floor. Ducting can also be laid for other services such as water, which will be connected at a later date. The best hardcore is usually obtained from a quarry. This limestone quarry produces aggregates for concrete. The quarry waste is screened to remove loose earth and used for hardcore. Ideally, the stone should be graded. In other words, it should contain particles of different sizes. This helps compaction and minimises the risk of future settlement. In some parts of the country, stone is not readily available and other materials have to be considered. In the past, broken bricks, crushed concrete and various industrial and mining wastes have been used as hardcore. These materials should be used with caution, however. Some may contain impurities, which over a long period can react with water, causing expansion of the hardcore or a chemical reaction in the concrete. Both can lead to cracking and lifting of the slab. Compaction is usually achieved by a small vibrating plate or roller. These machines are only effective if the material is laid in thin layers. Thick layers can't always be properly compacted, leading to future settlement of the hardcore and cracking of the slab. Although a good quality hardcore helps reduce capillary action and therefore rising damp, a damp-proof membrane is required by the building regulations. The cheapest form of membrane is polythene sheeting. To prevent sharp stones in the hardcore tearing the polythene, it's normally laid on a thin layer of sand or stone dust called blinding. The DPM also protects the slab above from any aggressive chemicals which may be present in the hardcore. The concrete is usually brought onto site ready mixed. It's a mixture of cement, stone and sand and can be produced in a variety of strengths by varying the proportions of the ingredients. When the concrete is in place, it has to be levelled and compacted. This is usually achieved with a heavy beam known as a tamp. Tamping levels the surface and expels surplus air and water. A tamped finish is fairly level, but not smooth enough to take vinyl tiles or carpet coverings. The concrete will set in a few hours and achieve its full strength after a few weeks. In hot weather, it can dry too quickly and crack. A temporary layer of sheeting will control evaporation and slow down the set. In cold weather, Hessian or special quilts can protect the concrete from frost. When the building is waterproof and weathertight, it's common practice to finish the slab with a screed made from coarse sand and cement. It can either be ready mixed or batched on site. If the mix contains too much water or too much cement, the screed will crack. Not enough, and it won't set or achieve adequate strength. On a clean concrete slab, the thickness should be about 40 to 50 millimetres. If the screed is less than 40 millimetres, it may dry too quickly and cracking will occur. To obtain a smooth, even surface, the screed is levelled with a straight edge and finished with a steel float. Some screeds are also compacted mechanically. Laying moisture-sensitive floor finishes cannot take place until the screed and slab are dry. When the DPM is laid below the slab, this can take several months. The problem can be partly overcome by separating the screed and slab with the DPM. The damp slab no longer affects the screed, which can then dry quite quickly. This sandwich membrane can be formed from polythene or a number of liquid solutions. Because the screed is separated from the slab, it needs to be slightly thicker to prevent the risk of cracking. Since the 1990s, most ground-bearing slabs have had floor insulation of some sort. Before this, uninsulated ground floors could account for 10 to 15% of total heat loss. There are a number of insulation options. Choice depends on the type of heating system, the nature of the insulation, and the preferences of the designer. If the insulation is installed below the slab, the concrete acts as a thermal store, helping to maintain steady temperatures in the building. The insulation, normally laid over the damp-proof membrane, is made from rigid polystyrene or foam. Some insulation materials are not affected by moisture and can be laid below the DPM. This type of insulation is slightly more expensive, but does away with the need for the thin layer of sand blinding below the membrane. If the insulation is installed above the slab, the building will respond more quickly when the heating is turned on. The insulation can be finished with a screed or with sheet materials such as chipboard. This approach is known as a floating floor. Chipboard is very sensitive to moisture, and in damp conditions, the boards can swell and disintegrate. To prevent moisture from the drying floor structure affecting the chipboard, a vapour check is usually required immediately below the board. This is in addition to the damp-proof membrane below the slab. To ensure the vapour check is continuous, it should have taped joints. In situations where the main DPM is above the floor slab, this additional vapour check is not required. The sheets of chipboard have tongued and grooved edges and are simply laid over the polythene. The sheets are not fixed down to the slab, although their edges are glued. In bathrooms and kitchens, where levels of humidity are high, it's wise to use a special grade of moisture-resistant chipboard to maintain durability. Temporary wedges can provide a gap of about 10 mm around the perimeter of the boards to allow for future thermal and moisture expansion. If a designer requires a screed rather than chipboard, it should be separated from the insulation boards by a thin slip layer. The screed may also need reinforcing with a thin mesh to prevent cracking. In some situations, the use of a ground-bearing concrete slab is not suitable. These include some clay subsoils, high water tables, and deep hardcore. If the hardcore is less than 600 mm deep, it's fairly easy to compact and the risk of future settlement is slight. However, where the depth is more than 600 mm, or where the slope of the ground results in hardcore of uneven depth, there's always a long-term risk of settlement. Clay subsoils, particularly where trees are present, are prone to shrinkage in periods of hot, dry weather. As the ground dries and shrinks, the ground-bearing slab may settle. Where trees are removed, the opposite problem occurs. The ground can expand and heave as the clay subsoil copes with surplus water no longer required by the tree. Where groundwater levels are high, traditional DPMs will not be adequate. Most DPMs are designed to prevent capillary action, not direct water pressure. High groundwater levels can also increase the risk of chemical attack, especially if the slab remains wet for long periods. In all these situations, it's preferable to use a suspended concrete floor, and nowadays most suspended floors are precast. Some developers consider that suspended precast floors reduce the risks of on-site errors, so they're common, even where ground-bearing slabs would be acceptable. In fact, more than 60% of modern ground floors are precast. In the mid-1990s, this figure was probably nearer 15%. A suspended ground floor is supported by the walls and is quite independent of the ground below. These floors usually comprise a series of precast beams supporting an infill of lightweight concrete blocks. The construction is very quick, and unlike traditional wet concrete floors, it's not affected by extremes of weather. The beams and blocks are grouted to tighten up the floor, help spread loads, and to provide a barrier for drafts and vermin. If the airspace beneath the floor is well ventilated, and if the ground is effectively drained, there's no need for a DPM. A floating floor of particle board or screed, both laid on insulation board, will complete the floor construction. On this site, the ground floor is partly precast and partly in situ. This floor, known as jet floor, is still based on a series of precast beams, but it has a polystyrene rather than concrete block infill. A lightly reinforced in situ concrete topping finishes the floor off. The polystyrene infill blocks are very light and easy to handle. They act as insulation, tucking under the beams to prevent the risk of cold bridging and subsequent condensation. The in-situ concrete topping is reinforced with glass fibre strands. If the floor is to carry heavy loads, say in a garage, steel mesh may be used instead. The floor could be finished with a traditional screed, but on this site, the concrete is going to be power floated. This will provide a finish smooth enough for carpets. The finished floor surface must be protected by sand until the building is finished. This film has traced the evolution of ground floors in houses over the last 100 years or so. Nowadays, the pressure to develop inner-city brownfield sites has led to a different approach. Multi-storey construction, possibly on contaminated or poor quality land, requires much more complex ground floor solutions.